Then the next one is magnitude of weight. And magnitude of weight and gravitational force interchangeable. Weight is a specific aspect of gravitational force. In this case, the gravitational force and weight are interchangeable. When we get to chapter 9 or 10, we'll talk about when gravitational force is not weight. Magnitude of weight is just the absolute value of this. The negative sign is the direction. The negative sign says down. Magnitude of weight is just the 30. And then comes the mass.
But so you say that the magnitude of weight is the absolute value of the gravitational force acting?
Yes.
Okay.
Yes. Now, the mass. Most people are usually taking 110, are heavy in the biological sciences. You're doing something related to biology or medical or something like that. I think that's typical. And I know biology uses mass and weight interchangeably a great deal. In physics, we don't get away with that. Mass and weight are two different things. They are related to each other, but they are not the same thing. My mass is about 100 kilograms. If I went to the moon, my mass is still 100 kilograms. My weight, though, would go from around 1,000 newtons to around 160 newtons if I were on the moon. So, weight is a type of force, the W there, and that's a vector quantity. Mass is a scalar quantity. Okay. The relationship between mass and weight is the following formula. That is the formula. Weight is equal to mass times the acceleration due to gravity. Little g here, acceleration due to gravity. It is not gravity. It's the acceleration due to gravity. There are three things that students tend to all call the same thing, gravity. This is one of them. Gravitational force, acceleration due to gravity, and the gravitational constant are all different aspects of the same thing. Gravity, huge topic. We're just dealing with these tiny little slivers of it. The weight would be 30 newtons. The mass we're trying to find, and G depends upon where you are. The world average is about 9.8 meters per second squared. So we'll emphasize that over here. Draw that back. So G, world average, is about 9.8 meters per second squared. It's 9.805 something. Hewitt, in the textbook, will often just make it simpler and say 10 meters per second squared. I refer to that as Earth 2. It's very similar to Earth, just slightly a little bit different. So if we're on Earth 2, G is 10 meters per second squared. Winston-Salem is 9.798 meters per second squared. This is the Winston-Salem value. At this point, they have, in essence, mapped the entire world. They did it in a grid pattern. You have to sort of interpolate it a few different places. But based upon that data, I got 9.798 meters per second squared for Winston-Salem. Also, before they went and flew the planes all over the world to try to map this out, they had these boxes located throughout the US. And the one in Winston-Salem was actually about, I think we're about the same level as, maybe a little bit down, Silas Creek. You've got Miller, Silas Creek coming this way. It's the next road that you hit. It tees into Silas Creek. In the median there, that is where it was buried. We have a better value for acceleration due to gravity than most places in the world, just because it so conveniently was put right out there. So on labs, usually under notes, I'll have let G equal, and if you see this number, because we're dealing with Winston-Salem. Now sometimes it doesn't matter a whole lot, and I'll just say go ahead and use 9.8, or there are a couple labs where I don't say anything at all, and then just use one of them. But if you ever see the let G equal 9.798 meters per second squared, that is coming from the specific value of G here in Winston-Salem. Or specifically here at Forsyth Tech. All right, so let's get to the math. So I have 30 newtons is equal to the mass times G, 9.798 meters per second squared. Now, it is unfortunate. This M right here stands for mass. This M right here stands for meters. We use M a lot. Unfortunately, you have to sort of pull from context which M it is. If the M is coming right after a number, it's probably meters. They're not always. Now, I've put the units in here. It potentially makes it look more confusing. Let me put it in a simpler way. Just the math piece of it. 30 is equal to 9.798 times M. This M is still mass. That's the math problem. How do you solve for M?
Can you divide by 9.798?
Yeah. We have multiplication going on here, and you have to isolate M by itself, so we have to get rid of everything, and the way you get rid of this is to divide, because it's multiplying, multiplication is undone by division. So divide both sides by 9.798. And so, on the right-hand side, I have mass. On the left-hand side, I've got 30 divided by 9.798. If someone would be kind enough.
3.061.
3.061.
Well, actually, no, you rounded to 3.062, sorry.
Okay. Now, questions on how we got that?
So the newtons and all the other units just go away?
That brings up the next step of what are the units? Well, I had newtons here, that's 30 newtons. So I did 30 newtons divided by 9.798 meters per second squared. The 30 divided by that is this. And now I've got to deal with somehow this newtons over meters per second squared. What is that? I'm skipping. So Newton over a meter per second squared, we can, here's the long way. It's perfectly legitimate, it's just, at some point, you'll be able to bypass this step. Or you'll skip it, not just bypass it, ignore it. Dividing by a fraction, same as multiplying by the reciprocal. So here we're dividing by fraction mark, just division, so newtons divided by meters per second squared is the same as a Newton times second squared per meter. So I could, as a unit here, put Newton second squared per meter. That is perfectly legitimate. However, a Newton is what is known as a derived unit. If you ever see me write the 3 bars like that, kind of like an equal sign, but with an extra bar, that means this is true by definition. It's not derived, it's that the powers that be sat down and they said, we are going to define a Newton to be this. A Newton is a kilogram times a meter per second squared. If you don't like it, you need to get into a position of power and change that. That is just the way it is. So when I divide both sides by meters per second squared, I'm left with kilograms. So my mass is 3.062 kilograms.
What does the 3 equal sign mean?
By definition, it is equal by definition. It's possible, I don't think this is used as much, but it's also, that symbol is sometimes used as well, an equal sign with a triangle over it.
I've never seen that one before.
Okay.
I have seen the 3
Okay.
before, but
Yeah.
I haven't seen that one.
They mean the same thing.
Okay.
The 3 bars is just easier to write than the equal sign with the triangle.
I agree.
And occasionally I see the equal sign and then by def written in very tiny print. All right. Hopefully that will help you with the lab, but if you have questions, of course, ask. Let's talk specifically about forces. There are basically 5 types of forces that we will deal with in this course. Later on, we'll add, well, it depends on the pace at which we go. Potentially, we're gonna add buoyant force or electric force or magnetic force. Probably won't get to magnetic, but, so we'll add a couple other letters as opposed to giving you the huge thing of which we'll only use this small piece of it. But this represents basically a checklist when you're going through doing a force diagram, which we'll get into more detail, I guess, a week from today probably. F, this F stands for friction. T for tension. O for other. I needed a vowel also. W for weight. N for normal. And weight, I'm going to parenthetically write gravitational force. So eventually you'll be given a problem, like I have a ramp, a box is sitting on it, draw the force diagram, and then you'll go through this checklist, figuring out which forces are involved. The symbol I use for friction is what I call the Baroque F. It's just basically a fancy F. Not everyone uses that. Some people will do an F with a subscript F. With parentheses F. That's just awkward for me. Weight, I use the lowercase w. Gravitational force, if I need it more generalized, F subscript G. Normal force, I use the letter Y because when I first learned this stuff in high school, that was the letter the textbook used. And we don't use capital Y for anything else. There's enough overlap, like, that we use Y for that. Tension, I used to use a capital T, but later on in the course, we get to a point where I need tension and period is a capital T. And so instead of using capital T up until that point and then going, all right, now we're switching it for tension, F sub T. And other is problem specific. Questions to you? All right.
Can you explain just one more time what you were saying about, like the difference, like looking at weight in this class as opposed to like biology? You stated it earlier and I was
If
listening.
I said I had a 3 kilogram box,
Uh-huh,
the mass is 3 kilograms.
yeah,
The weight is not 3 kilograms.
okay,
Kilograms is not a unit of weight.
okay.
That's the main thing. I've
Okay,
had
cool.
a number of people where, even at the test, when we get to the test, and I say, I've got a 3 kilogram box, what's the mass? What's the weight? And then they mess up on the weight because they write down 3 kilograms.
Okay.
And then sometimes do strange things where they take that, divide by 9.8 to get the mass which was given.
So
If
like-
that, oh, sorry.
No, I was gonna say, so just like in simple terms, what is the difference between weight and mass?
Weight is a force that is caused by two masses. Two masses are attracted to each other, and it's the force with which they are pulled towards each other. Mass is a representation of the amount of inertia an object has, or a representation of how much stuff is in them.
And you said weight is a vector and mass is not, right?
Correct.
Okay,
Very much.
that's helpful, thank you.
All right, so. Hidden these, now I'm gonna throw definitions at you, I apologize for that. Next Wednesday, we'll go into the force diagrams. It's helpful if you watch those videos by then, but it's nice if I could do these and then go straight into the force diagrams. We will not do that today, just for time reasons. But it's all in the video. All right, so the requirement. In other words, what has to be in place in order for these forces to exist? There must be desired relative motion. And there must be contact. We're not worrying about air resistance. What? It's perfectly plain scribble. Desired relative motion.
What does that mean?
All right, so. First off, the contact bit, this disc right here, there's absolutely no friction between this disc and the carbon. They have to actually touch. Desired relative motion, as I walk this way, this disc stays with it. But if this book were frictionless, if the book's frictionless and then I start moving that way, what would the disc do?
Slide off, right?
Which way would it slide?
Which way are you walking? You're walking that way?
I'm walking that way. Correct, yes. Saw a couple people with their fingers in the right direction, yep. See if we can get one more person pointing in the right direction. Ooh, got several of them, excellent. So it would slide that way. So it wants to move, it wants to actually stay where it is, but relative to what it's touching, it wants to slide that way. And so it wants to go, that's the desire. Relative motion, it does want to move relative to this, it wants to move that way relative to the book. And friction says no. Friction is going to oppose that. Since this wants to slide that way relative to the book, friction says, I'm going to apply force on you that way. And that's why the disc moves, is because of friction. That is not the look of someone who completely understands. Am I just reading you? Am I?
Me?
Yes.
I don't understand.
Okay. At least well enough for now. Tension requires basically pulling, usually with a rope, a string. That's the word string. Chain, whatever you happen to be pulling with. Weight, the requirement, two masses. And the generalized gravitational force requires two masses, any two masses. There's a gravitational force between each of us. There's a gravitational force between you and the desk, between you and the chair. It's not much of a force, because I think most of us can easily get up and leave. So the gravitational force is relatively weak, so we're going to ignore all the little ones. We just care about the big ones, unless I'm dealing with tiny masses, but that's later on. So that's true for this and weight by nature. Weight also has the requirement that one mass is huge and one mass is near the huge mass and is small. In other words, I have a weight because I'm a small mass next to the earth, near the earth. An elephant has weight because it is a small mass next to the earth. The mass is huge. We're talking about planets, moons, stars. And near, my weight does not change significantly, by the time you get 100 kilometers up, my weight has been reduced by 8% or so. Normal force requires contact. It's a pushing force. Why are you not falling through the chair? If the chair were not there, you would fall.
Because the
So-
chair's pushing us back up from like the center of gravity? I don't know if the center of gravity is
More detail
necessary.
than we need, but
Okay.
because the chair is pushing up on you, that's the normal force. I think Hewitt calls it the support force. The normal force is normal is a math term here. Anyone know what the math term normal means? It means perpendicular. The normal force is perpendicular to the surfaces of contact. The floor is pushing up on me. It's not going to push at some angle. The floor, if we assume the floor is level, the normal force will push up on me. I'm pushing down on the floor with a normal force. The chair is pushing up on you. You're pushing down on the chair. I'm leaning against the wall. The wall's exerting a normal force on me that way, because it is perpendicular to the surfaces. I'm exerting a normal force on the wall in that direction. Other. Other is, the requirement is you have a force of which you don't know what's causing it, or from a physics point of view, don't care. I'm not talking about you personally, whether you care or not. It's a matter of, from a physics point of view, does it matter? And the problem I did over there, where I had a box with a 3 Newton force pushing on it, what's causing the 3 Newton force? It doesn't matter. It did not matter for any of that stuff that we did. That is an example of other. Other typically shows up in a textbook problem, where they just say there's like force acting on the object in some direction, 3 Newton force acting to the right, 4 Newton force acting up. You don't know what's causing those forces, you don't need to know. That's an example of other. And questions?